This video should help you get started with the follow-up to the relative mass lab simulation, which you should have already completed the first part. So I want to go over the background information and then do a couple calculations to get you started, and then you can take it from there. So at this point in the activity, we determined the relative mass of the hardware elements, and we scaled up the quantity of hardware pieces using the concept of boxes of hardware pieces. We didn't know how many hardware pieces were in a box, but it was still a useful concept because we could measure out equal quantities of the hardware pieces when needed, and we did a couple calculations where we did that. It was all based on the relative masses that we found in our fake periodic table of hardware here. We never did measure the mass of an individual piece, but using samples of equal quantity, we were able to figure out the relative masses of the different pieces of hardware. So this is also how chemists typically work with real element samples using a quantity called a mole. A mole simply represents a scaled up quantity of atoms that's more convenient to measure. A mole of any substance contains the same number of particles, just as our box of hardware always contains the same number of pieces. At this point, you might wonder, why did they call it a mole? It's actually from the Latin word mole, which means a lump or a mass. So it's a special lump, a special mass that always has the same number. In the first part of the simulation, we did not know the number of pieces of hardware in a box. Likewise, for decades, chemists did not know the actual quantity of particles in a mole. Even so, it was still a useful concept for comparing the number of particles involved in chemical reactions. Not until the invention of the mass spectrometer was it possible to measure the mass of individual atoms or molecules. So this is a piece of technology that came along in the early 1900s that expanded our ability to measure very small things like molecules and atoms. Once you could make the measurement of an individual atom, the quantity of particles in a mole could be determined. The extension that follows will model this process with the hardware analogy. So I have a link here that takes you to a page. Let's go ahead and take a look at it. You can read through this. This is all about this technology, mass spectrometry. If you do nothing else, watch this video. It does a really good description of how mass spectrometry is used to measure the mass of very small particles. You can read the rest. There's a second video. Don't really need to watch that one, but the point being, or the take-home point from that, is a mass spectrometer could actually tell us the mass of an individual atom. So the way we're going to model that in the activity is to say, let's say you have a really accurate, precise balance. This is going to play the role of a mass spectrometer, and we find the mass of an individual small washer to be 0.6519 grams. It turns out that this is a good actual measurement of the small washer, so it is representative of what you were actually measuring in the lab. So using that value, the mass of one small washer, we want to do some counting. We want to do some calculations related to that. So number one says, using this value, calculate the number of small washers in a box. Use conversion factors, and remember that 1 kilogram equals 1,000 grams. Start with the fact that one box of small washers has a mass of 1.0 kilograms. So again, 1.0 kilograms was the mass It's the mass of one box. So that's going to be what we start with. Since our per small washer value is in grams, instead of starting with 1 kilogram, I'm just going to say that I have 1,000 grams of small washers. And I want to figure out how many pieces are in 1,000 grams. So with my conversion factor set up, I want to use a conversion factor. I want to cancel grams of small washers, and I want to end up an actual quantity of small washers. So I'm just going to put SW for my unit. And I know that one small washer from the data given has a mass of 0.6519 grams. So that's set up. If I set it up this way, I would cancel grams of small washers, and I would end up in the count of small washers. Mathematically, what am I doing? I'm taking 1,000 grams and dividing it by the gram amount of 1, which should make sense, right? I want to divide it up and see how many of these gram values fits in 1,000 grams. So if you punch that into your calculator, 1,000, you could multiply by 1 if you want, but it's still 1,000. 1,000 divided by 0.6519, you will see a value of 1,533.977, and even maybe some additional digits. That is essentially, if I go to the nearest whole unit, and I'm going to assume I have some whole washers only, I don't have a washer that's cut in half, that is essentially 1,334 small washers in one box. Okay, it's kind of a random number because of the way we initially defined a box. We just said we need to invent a count. We're going to say it's the amount in 1 kilogram. So it shouldn't surprise you too much that it is just kind of a random number. And that's true of the mole value as well. It's not a nice round number, and that's because, again, the way the mole value was initially defined was a similar process. The initial meaning was how many particles are in 1 gram of hydrogen, or sorry, how many atoms are in 1 gram of hydrogen. They didn't know what the value would be, and so it is not a nice round number. So what I can say is I know that small washer was kind of my standard with a relative mass of 1.0. We defined a box of those as having a mass of 1,000 grams. And now we can say that there's 1,534 particles in a box. We were given the mass of one particle. I'm going to go ahead and put the units on here. Grams. So what can I say about the rest of these here? What can I say about the medium washer and the medium hex nut and the medium bolt and so on? Well, I can go back to my periodic table of elements to note the relative masses. It was 1.2 for the medium washer, 2.0 for the medium hex nut, and 2.3 for the medium bolt. Okay. Again, scaled up by 1.2, 2.0, 2.3, the mass of one box. This is stuff that we already knew. Those would be our values scaling it up to a box. And then what I also know is that a box is always the same number of particles. So I can fill in 1,534 for all of these. That was the common thread throughout defining a box. It had the same quantity each time. So to find the mass of one particle, think about what we need to do. We need to take the gram amount and divide by the number of particles. We did that a slightly different way up here, but you should check that if you take 1,000 grams and divide by 1,534, that you do in fact find a mass of one particle of 0.6519. Now I can do the same thing right down in this column, total mass divided by particles, to get the mass of one particle. You should find that whatever the mass is here in grams, it should be 1.2 times as massive as the 0.6519 gram small washer. So you can do kind of a double check here. Divide grams by pieces, and then find that those individual pieces do in fact have a relative mass of 1.2, 2.0, 2.3, and so on. So hopefully that's enough to get you started on that table. I'm going to let you try the next page of calculations on your own. Highly recommend using conversion factors to do that, and you'll use some of the values in this table to do that as well. Good luck with your calculations. Bring your questions to class, and I will help you out when I see you next.